All right, for today's lesson, 3.4, we're going to go ahead and solve quadratics by factoring and square roots. Last class we solved quadratics by using the quadratic formula. And so just as a reminder, there's a few words that are interchangeable. So when we solved, we found solutions, but those really mean the same thing as x-intercepts, roots, zeros. So get comfortable with the fact that these words get interchanged all the time, especially on things like an SOL or an SAT. Figure out which of these words makes the most sense to you and just get used to changing them. So each time if I were looking at this and it said solve this quadratic, in my head I would think, okay, I have to find the x-intercept. I have to find where the graph crosses the x-axis. So we're going to be doing this in ways that we've already used before. We're just going to be putting them together. So for example, factoring, if that's something that you want help with, you're going to want to look back at your 2.2 and your 2.3 notes. So in 2.2, we talked about how to find a GCF, how to factor out a GCF. We looked at if we had something with 3 terms, we looked at how to find the GCF first, how to set up the number puzzle, and so on. So we're going to be using these exact same steps again today for factoring. So if you need to look back at these notes, have them open, that way you can follow the steps really easily. We also looked at factoring special types in 2.3. So the ones that are going to be most useful today, these are the 2.3 notes that we did. The most useful ones for today are going to be the difference of squares. So we'll kind of reinforce that again today. So once again, if you think that's something you're going to want reminders of, just have the notes out next to you, and that way you can kind of reference them. The last thing is, since we're finding x-intercepts where a graph crosses the x-axis, we've actually done that before. We did that in the 2.6 notes. So I'm just going to show you. In 2.6, once we factored and we found our factors, to find the x-intercepts, we just took each of those factors and put their y value equal to 0. And that was because any point that's on this x-axis has a y value of 0. So if I put y equal to 0, what I'm solving for are the x values that are going to be on that x-axis. So when we solved these two factors, we got an x-intercept of -1 and an x-intercept of +3. So we've actually essentially done this before. This is exactly what we're doing today. We're factoring to find the solutions, to find the x-intercepts. So we're going to do a couple of examples of that, solving by factoring, and then we'll look at solving using square roots as well. So let's start with factoring. Specifics of how to factor are in your past notes, but I will put a couple of notes about how to solve by factoring. So the first thing that you want to do is make sure that your equation is in standard form. And as a reminder, standard form is ax squared plus bx plus c. You'll know if it's in standard form because all of your terms will be on one side of the equal sign and the other side will have nothing on it. So if it's not in standard form, you'll want to move terms across the equal sign to put them all together and put it in standard form. After that, you're going to factor as much as possible. Oops. And so reminders of that are in the 2.2 and 2.3 notes. So we'll be looking for a GCF first, and then we'll be using the same steps that we did there. From there, we're going to set each factor equal to 0. And that's because the y value is 0 on the x-axis. And from there, we'll solve. So take a moment, pause this video, make sure you've got these steps down because they're the ones that we're going to be using over and over again for our examples. So I'll pause for a little bit as well, but take your time, make sure you write these down. So we're going to look at 4 examples of solving by factoring. Once again, if you're still writing down the steps, take a moment to pause this video and get those steps down. So in these examples, the direction each time is just to find the zeros. And zeros are just another way of saying find the x-intercepts, find the solutions, find the roots. They all mean the same thing. So essentially we're just going to find the x-intercepts. But once again, get used to and comfortable with those words being used interchangeably. So we're going to go ahead and find the zeros for all of these different examples. And we'll start with this one here. So if I think about my steps for factoring, and I'm just going to have the 2.2 notes off to the side here so we can reference them. My first step is always to look for a GCF. And I want to check the variables, I want to check the numbers. So I'm looking at these 2 numbers and I'm noticing that they're both even. They're both definitely divisible by 2. So part of my GCF is a 2. Sorry, this should have an x in it. The other thing that these 2 things have in common is an x. So the greatest common factor is a 2x, and factoring out a greatest common factor is essentially like undistributing. What I'm going to do is now I'm going to divide each of these things by 2x, and I'm going to say what's left over. So if I have 2x squared, and I divide it by 2x, 2 divided by 2 is going to give me 1, and x squared divided by x gives me x. So now if I take that negative 24x and I divide it by our greatest common factor, by 2x. So this is the part I'm showing you in pink, but normally this is the part I kind of do in my head. You always have the option of doing it in your head as well. So negative 24 divided by 2, that's going to give me negative 12, and x divided by x means there would be no x's left. I'll know this is right if I can distribute back out and get these 2 terms. So 2x times x is 2x squared. So that is definitely right so far. 2x times negative 12 gives me negative 24x. So that's also correct. And I'm noticing that these things are not going to factor further. If I look at what's in the parentheses, this is no longer squared, so it's no longer a quadratic, and it only has 2 terms. So this is an example of one where it can't factor further after taking out the greatest common factor. So since we've factored as much as possible, we're just going to set each factor that has an x equal to 0. So my GCF, that's one of my factors, and I'm noticing it has an x, which means that's going to help me find one of my x-intercepts. I'm going to put it equal to 0. My other factor is x minus 12, and I'm going to go ahead and put that equal to 0 as well. And if I solve each of these separate from each other, this is my clue that I'm going to have 2 different x-intercepts. So I'm looking at this, I'm thinking about solving means doing inverse operations. So order of operations is GEMDAS. When I solve, I want to do the inverse of that. So if I write GEMDAS backwards, this is what it looks like. So I would add or subtract first, then I would multiply or divide, and then I would deal with exponents and grouping symbols. So I'm noticing this is multiplication, so the inverse is going to be dividing. So one of my x-intercepts has an x value of 0 when I put the y value equal to 0. So one of those x-intercepts should be at the origin. This second equation, I'm noticing I have minus 12, so I'm going to go ahead and do the inverse. I'm going to add 12. So this other x-intercept should have an x value of 12 and a y value of 0. So I'm going to go ahead and show you on Desmos that this really is where this graph is crossing the x-axis. So if I go ahead and switch over to Desmos, this is the first equation that we just did. As you can see, one of my solutions is at 0, 0, and I'll zoom out a little bit so you can kind of see the whole parabola. This is a really crazy looking one. It goes all the way down past -70. But I'm just focusing on the x-intercepts for now. So I'm going to zoom back in so we can see where it's crossing the x-axis, and that's happening here at 0, 0 and at positive 12, just like we found. And I'm going to go ahead and link this Desmos graph in Schoology. That way you can look at all of these the way that I'm showing you later on if you need to. So we just saw that that really is where our graph is crossing the x-axis. So we're going to go ahead and try a few more. Each time we're using the exact same factoring steps as we did in the 2.2 and the 2.3 notes. So I'll try to keep reminding you of those steps, but it might help to look back at those as well. So this next one that we're going to factor is x squared plus 3x equals 18. I'm noticing that this is an example of an equation that is not in standard form. All my terms should be on the same side of the equal sign, and they are not. And so I always want to leave x squared where it is. I want to bring all my other terms to the same side with it. So that positive 18, I'm going to use inverse operations, and I'm going to go ahead and bring it over. So I have x squared minus 3x, sorry, plus 3x, and then minus 18. And there's nothing left on that side of the equal sign. So that's my clue that it is in standard form now. I'm going to go ahead and start to factor this trinomial. A trinomial is something that has 3 terms. And so the 2.2 notes can help with that. I'm going to start by looking for a GCF. So I'm noticing that these 3 terms, there's no number that divides into all of them. There's no variable that they all have in common. So this one doesn't have a GCF. So next I'm going to set up my number puzzle. And in that number puzzle, I'm going to go ahead and do the A value times the C value. So my A value here would be 1. My C value here would be negative 18. So 1 times negative 18 gives me negative 18. In the bottom of my puzzle, I'm going to put my B value, and my B value is that positive 3. And I'm looking for 2 numbers that multiply to be this top. So I'm looking for 2 numbers that give me negative 18. Those same 2 numbers should add up to be the bottom number. So take a moment, pause this, see if you can find the solutions to that number puzzle. I'll leave this here. So the 2 numbers that multiply to negative 18 and add up to positive 3. And you should get negative 3 and positive 6. So negative 3 times 6 is negative 18. Negative 3 plus 6 is positive 3. So those are the 2 solutions I want. Those 2 solutions are how I'm going to split up this middle term. So I'm going to rewrite, and instead of 3 terms, I'm going to have 4 terms. I'm going to split up this middle term into a negative 3x and a positive 6x. So what I mean by that is x squared would still be the same, but instead of 3x, I'm going to put negative 3x and positive 6x, and that negative 18 would still be there. So instead of having 1, 2, 3 terms, I have 1, 2, 3, 4. And those 2 middle terms come from my number puzzle solution. Notice that if I combine these together, negative 3x and positive 6x give me positive 3x. So I haven't changed the value of this quadratic. All I've done is changed the way that it looks, and that way I can go ahead and split this and factor by grouping. I'm going to find the common factor for each half. So take a moment, pause this video, see if you can go ahead and factor each of these halves. So I'm noticing for the first half here, there's no number that divides into both of them besides 1, but they have an x in common. So their GCF is going to be an x. If I divide this term, x squared, if I divide out an x, I'll have an x left over. If I take negative 3x and I divide it by x, I'll have negative 3 left over. And I know this is right because a greatest common factor, I should be able to distribute it back in and get both of these terms. So x times x gives me x squared, x times negative 3 gives me negative 3x. So we're going to do the same thing for this other half here. And I'm noticing my leading coefficient is positive, so whatever my GCF is, it's definitely going to be positive. And I'm noticing they don't have any variables in common, but they're both divisible by 6. So my greatest common factor is going to be a 6. And I'm going to undistribute that. I'm going to divide that out from both of them. So 6x divided by 6 would be x. Negative 18 divided by 6 would be negative 3. And at this point, you're basically done factoring. You're just going to write out your factor. So I'm going to move this. And you have a way to check to see if what you've got so far is right. So if you've factored this correctly, what's in parentheses on each side should be the same. And I'm noticing it is. So our factors for this equation, one of them is going to be x minus 3. It's that part that's the same in the parentheses for both of them. My other factor is going to be the GCF from each side put together. So x and positive 6. That's my other factor. And just as a reminder, you can check to see if your factors are right just by multiplying them back out. So I'm going to do it just for this one. But if I were to start distributing back out, x times x would give me x squared. X times 6 would give me positive 6x. And I'm doing this on a sticky note just because this isn't part of the notes, but I wanted you to see that you can check your work along the way. So I've distributed the x to both terms. Now I'm distributing that negative 3. So negative 3 times x gives me negative 3x. Negative 3 times 6 gives me negative 18. And notice what I have here is what I have exactly here. And so I'm going to work on combining these like terms now, and that's going to give me x squared plus 3x minus 18, which is exactly what I have here. So that's definitely the two factors for this quadratic because it gets me back to the original. So you can always check your factors by multiplying back out. So we put our equation in standard form to begin with. We've factored as much as possible using those steps from the 2.2 notes. So we're just going to go ahead and set each of our factors equal to 0. That way we're finding those x-intercepts for the graph. So I'm going to go ahead and say that this factor of x minus 3 equals 0. This factor of x plus 6 also equals 0. And so if I solve this first one, I'd be adding 3 to both sides. So I'll get x equals 3. If I were solving this second one, I would subtract 6 from both sides. And so I'll get x equals negative 6. So this first factor tells me that I should have an x-intercept of 3, 0, an x value of 3, and a y value of 0. This second factor tells me that I should have an x-intercept at negative 6, 0. So we're going to go ahead and look at the graph for this one just to verify that this is really where it's crossing the x-axis. And once again, I'll have this Desmos graph linked in Schoology for you. All right, so I'm going to turn off the last one. Here's the one that we just solved. So once again, this is a crazy looking graph. It's a really skinny parabola that goes very far down, so much so that I'm not even going to show it. The only part we're concerned about right now is where it crosses the x-axis. And so I can see in this case that it's crossing at positive 3 and negative 6, exactly like what we found. All right, so take a moment, pause this video, think about whether you need help with factoring, if there are any things so far that don't quite make sense. And we're going to look at 2 last examples of solving by factoring. Alright, so the first one is going to be 5x squared plus 13x equals 6. And the second one is going to be 25x squared minus 16. All right, if we look at this first one here, I'm referencing the steps that are off screen, you can't see them, but the first thing I want to do is make sure I'm putting this in standard form. So take a moment, kind of quiz yourself, see if you can figure out how to get all the terms on one side of the equal sign. So if I think about inverse operations, I'd be subtracting 6 from both sides. And so my new equation in standard form would look like this. And I would have nothing, I'd have 0 on that other side of the equal sign. So take a moment, pause this video, and make sure that you can factor this quadratic. If you need to, look back at those 2.2 steps in the 2.2 notes. But you should be looking for a GCF first, and then setting up your number puzzle. All right, I'm noticing there's nothing that divides into all three of these. So they don't have a number in common, they don't all have x's, they don't have an x in common, so there's no GCF for this one. So we're going straight to the number puzzle. A times C, so 5 times negative 6, that gives me negative 30. My B value is positive 13. And I'm looking for two numbers that multiply to negative 30 that add up to 13. So pause for a moment, see if you can find the solutions to that number puzzle. A common mistake here is saying 10 and 3. 10 and 3 add up to 13, but 10 times 3 gives me positive 30, not negative 30. The solutions to this are actually 15 and negative 2. So 15 times negative 2 gives me negative 30. 15 minus 2 is going to give me positive 13. And so I'm going to work on rewriting this middle term using these two numbers instead. I'm going to split it apart. So I'll still have 5x squared, but instead of 13x, I'll have positive 15x and negative 2x. I'll still have that negative 6. So the number puzzle helps us figure out how we're splitting up that middle term. Notice that if I combine 15x and negative 2x together, they give me 13x's. So these are equivalent to each other. I haven't changed the value. I've just changed the way that it looks so that I can split it and find the common factor for each half. So pause for a moment, quiz yourself, and see if you can factor this now. I'm noticing that both of these terms are divisible by 5x. So if I divide them each by 5x, I'll have an x left over and positive 3. And I know that's right because if I distribute back out, 5x times x gives me 5x squared. 5x times 3 gives me 15x. For my second half, I'm noticing my leading coefficient is negative. So I'm definitely going to have to factor out a negative. And I'm noticing that both of these things are even. They're divisible by 2. So if I divide negative 2x by negative 2, just an x will be left over. If I divide negative 6 by negative 2, I'll have positive 3 left over. And I know that's right because if I distribute back out, negative 2 times x is negative 2x, and negative 2 times 3 is negative 6. So we're done with the factoring. We just have to write our factors now. One of our factors is what's on it's the same on both sides, that x plus 3. Our other factor is taking the GCF from each side and putting them together. So the GCF for this side is 5x. The GCF for this side is negative 2. And I'm not going to show it this time, but you could check your factors just by multiplying back out and making sure it really does give you these three terms. But these definitely are correct. So this is what we did in 2.2, was factoring. We need to solve now. We need to find the solutions, or the x-intercepts. So I'm going to go ahead and take each factor and put its y value equal to 0. And that way I'm finding the x-intercept, because an x-intercept is a point where the y value is 0. It's on the x-axis. So if I solve this first one, I'm noticing I would take away 3 from both sides. So I'm going to get an x-intercept of -3. For this one, I would have to add 2. And then this is multiplication, so I would be dividing by 5 afterwards. And we're going to go ahead and check the graph in just a moment. But just to show you that these two x-intercepts, we would want to leave our answer as a simplified fraction for this one. But on the graph, I think it's going to show us a decimal. So I just want to show you that 2 divided by 5 gives me 0.4, and we'll see that on our graph. So I'm going to switch over to Desmos. I'm going to go ahead and turn on the equation that we just looked at, and notice it's crossing at -3 and at 0.4, or 2/5. So we just saw from the graph that these are definitely the correct x-intercepts. For this last one, I'm noticing that I have nothing on one side of the equal sign, and then all my other terms are together on the other side. So this is my clue that this is already in standard form. And I'm noticing that this is similar to some things that we saw in the 2.3 notes. So these are a special type of quadratic. This is an example of a difference of squares, because we have two perfect squares separated by a different sign, a minus sign. There's no common factor that divides into both of these. I'm not going to be able to factor anything out, but the shortcut is I can take the square roots of each of these, and that'll give me my two factors. So the square root of 25x squared, well, the square root of 25, that's 5, and the square root of x squared, that's x. The square root of 16 is 4, and the special pattern is that these are just going to have opposite signs. And I could check these by multiplying them back out to verify that it really does give me these two terms. So two perfect squares separated by a different sign, you can take the square roots of each of them, and that'll give you your two factors. So that's from the 2.3 notes. That's the factoring part. What's new today is taking those factors and setting their y value equal to 0 so that we can solve and find the x-intercepts. So I'm noticing that using inverse operations, I would take away 4 from both sides. This is multiplication, so the inverse would be dividing. So that's going to be one of my x-intercepts. If I solve this one, I'm adding 4 to both sides. And this is multiplication, so I'm going to divide. So this graph should cross the x-axis in 2 different places. Once again, Desmos is going to show those as fractions, or sorry, as decimals. So this should be -0.8 and +0.8. And we're going to take a look at that graph now. So I'm going to turn off the last one and turn on this one. So notice that it's crossing here at -0.8 and +0.8. So those are my two solutions. We also call those roots, we call those zeros, we call those x-intercepts. So all of those words get used interchangeably. So that's how to solve by factoring. It's taking a lot of what we've done in the past and kind of just putting it together. We're going to talk about how to solve using square roots now. I've run out of space on this page, so take a moment, see if there's anything that you still need to write. You can pause this video if needed. And I'm going to go ahead and flip over so we can solve using square roots. And then once again, just as a reminder with vocabulary, when it's telling me to solve, it's telling me to find solutions, which are also known as x-intercepts, roots, and zeros. So you'll see the directions. They might say find the solutions. They might say find the x-intercepts. And you have to know that that still means we can use this method. So the way that we solve using square roots, and once again, this is actually something you've done before, you've just not done it in this context. We're going to essentially solve it like an equation. So we're going to treat it no differently like an equation. This is usually going to be easiest when we have an equation in vertex form. Vertex form is just another way of saying transformation form. It's what I have written on the board. That's the one that exists for all of our equations this year. So that would be if I had ax minus h squared plus k. So that's what transformation form looks like, or vertex form. So solving using square roots is easiest if I have something in vertex form, or when the b term is missing in standard form. So instead of ax squared plus bx plus c, it would just be ax squared plus c. So solving using square roots is easiest in these two scenarios. So if I have one of these situations, the way that I will solve is I will set my y value equal to 0. And that's because x-intercepts have a y value of 0. Any point on the x-axis has a y value of 0. And then we're going to use inverse operations. So order of operations is GEMDAS. If I write that backwards, it looks like SADMEG. So this is the order that I solve equations. And we're just going to solve. And you guys have solved lots of equations before, so this is really going to be no different. The one thing we do want to be careful of, and I'm going to keep highlighting it in orange anytime we encounter it, but if you take the square root of both sides of the equation, so both sides of the equal sign, there are going to be two solutions from that. And I'll show you what I mean with our first example. So there's going to be a positive and a negative solution to that. So when we encounter that, I'll highlight it in orange so you can see what I mean. But take a moment, pause this video, write down these steps. Feel free to put them in your own words, but this is what I'm going to be referencing each time we look at an example. So I'll pause for a moment as well, but it might help to pause the video. And it actually doesn't matter what the variable is. I have an h here, but I'm just going to go ahead and change it to an x. But it could technically be any variable, doesn't matter. All right. So I'm noticing this is in standard form, right? All of my terms are on one side of the equal sign. And I'm noticing it's an example of an equation in standard form, but it's missing bx, it's missing that b term. So this is an example of one that would be really easy to solve using square roots. This is something I could also really easily factor, but just to go over these steps, I'm going to go ahead and choose square roots as the option. So I'm going to start by setting my y value equal to 0. And that's because anything on the x-axis has a y value of 0. And next I'm going to start using inverse operations. So I'm going to start with any adding or subtracting first. So I'm noticing that minus 64, so I'm going to go ahead and do the opposite. I'm going to add 64. Next I'm going to go through and do any multiplication and division. So I'm noticing I have 4 times x squared, so I'm going to do the inverse, and I'm going to divide by 4. Alright, so now I'm going to work on any exponents. So I have an exponent here. The opposite of squaring something, the inverse of squaring something, is taking the square root. And whatever I do to one side of the equal sign, I have to do to the other. And this is what I was talking about. There's actually going to be 2 solutions that come from this, a positive answer and a negative answer. And the reason for that is I'm looking for any number that when I square it gives me 16. And in this case, positive 4 and negative 4 both work. 4 squared gives me 16, but negative 4 squared also gives me 16. So this is always going to happen. When you get to the point where you're taking the square root of both sides of the equal sign, there's going to be a positive and a negative answer to that. So you just want to add that in to remind yourself. So our equation, what this means is that our x-intercepts should be at 4, 0 and at negative 4, 0. You can leave your answer like this right here, but I'm just writing this out just so you can show, or you can check on the graph that we're about to look at. So once again, things that you've done before, you're just solving equations. And then the only thing that might be new today, although this did come up in geometry, is that if you take the square root of both sides, there's going to be 2 answers that come from that. So we're going to go ahead and go over to Desmos. We're going to take a look at this graph, and we're going to see that it crosses at 4 and negative 4. So I'm going to turn off the last one we looked at. Here's the one that we just did. So once again, if I zoom out, you can see this is a quadratic that dips down really far. That vertex is really far down. So this is one where solving by graphing would not be very helpful, but I can see that it's crossing here at negative 4 and positive 4. So notice that any point on this x-axis has a y value of 0. And that's why when we're solving, we put our y value equal to 0. So that's our first example. It might help to pause for a moment, double check your work, maybe work through anything else that you still need to. And I'm going to go ahead and start to show another example in just a moment. In this second example, I'm noticing that this is an example of a quadratic that's in vertex form or transformation form. I can see that the a value would be a negative 1/2, and that's my clue that if I were to graph this, this would be an upside down U shape. It'd be an upside down parabola. I can see my h value is a negative 8. I can find my k value as well. So this is an example of something in vertex form. So this would be really easy to solve using square roots. So I'm going to go ahead and start solving in that case. If I were to put all my terms on one side of the equal sign, I would have my y value equal to 0. But since my goal is to get x by itself anyway, I'm just going to go ahead and leave this as is and start doing any addition or subtraction first. So I'm noticing that plus 5, I'm going to go ahead and take away 5 from both sides. Next, I'm going to deal with any multiplication or division. And I'm noticing that this whole thing is being multiplied by negative 1/2. So So I'm going to go ahead and multiply by the reciprocal, which would be negative 2 over 1, or just negative 2. If I imagine negative 2 over 1 and multiplying out, a negative times a negative would give me a positive, and I'd end up with 2 over 2, and 2 divided by 2 just gives me 1. And so you can write in a coefficient of 1 here if that's helpful, but normally you won't see that. But that's why using negative 2 over 1 undoes that fraction. And then 4 times negative 2 gives me negative 8. Next, I'm going to move on to exponents. So the inverse, or the opposite of squaring something, is taking the square root. And as soon as I take the square root of both sides of the equal sign, I need to remind myself that there are two solutions to that. So there's going to be a positive and a negative solution there. And I apologize, I just realized that I wrote down the example wrong. This was supposed to be a negative 9. Sorry about that. So then let's change this. Negative 9 minus 5 would give me negative 14. And then negative 14 times negative 2 will give me positive 28. Sorry about that. It's not changing any of our steps, it just changes what the value of this was each time. So negative 9 minus 5 gave us negative 14, and negative 14 times negative 2 is going to be positive 28. So we were at the step now where we were undoing that exponent by taking the square root of both sides, and we just need to remember there's two possible solutions that come from that. So if I write out what I have on this side of the equal sign now, square roots and squares cancel each other out. So I'll have x plus 8 on that side of the equal sign. And then I'm going to have a positive and a negative square root of 28. And I just want to go ahead and remind everybody of how we simplify square roots. So using those same steps from previous lessons, 28 is not a perfect square, but I want to find the biggest perfect square that fits into it. And in this case, it happens to be 4. So I can think of the square root of 28 is the square root of 4 times the square root of 7. If I multiply those back together, I have 28, so I haven't changed the value. And that way, when I take the square root of 4, that's just a 2. The square root of 7, that's not a perfect square, so it'll still be in there. So I'm going to replace the square root of 28 with 2 root 7, just like I showed off to the side. So we dealt with the exponents. So what that meant is what was inside that grouping symbol is now outside of the grouping symbol. If I want to get x by itself, I'm going to have to subtract 8 from both sides. I'm noticing that 8 is not the same kind of radical as this. It's just a constant, a regular number. So I would have to go ahead and say that negative 8 plus and minus 2 root 7 is where my final answer is going to come from. For a test without a calculator, this is as far as you could go. You could even write it as 2 separate answers if you want. I could say negative 8 plus 2 root 7 is one of my answers. And I could say that negative 8 minus 2 root 7 is going to be my other answer. So for a test, this is as far as you would be able to go without a calculator. Just like we saw with quadratic formula. There were some of them that all you could do is simplify the radical as much as possible, and that would be it. But since we're going to check this on Desmos, I'm going to go ahead and show you the numbers that we would get for these, just so we can verify that it's right. So if I do negative 8 plus 2 root 7, so this first one here, that's going to give me about, so I'm going to go ahead and circle these just because that would be our final answer for a test. But so we can check on Desmos, this would be about negative 2.708. And now I'm going to do negative 8 minus 2 root 7. And I have an extra minus sign there, so I'll get rid of it. And so that would be approximately, or about, because I'm rounding, negative 13.29, and I'm going to round this up to a 2, but it might look different on Desmos depending on how they round. So at about negative 2.7 and at about negative 13.3 is where we should see it cross the graph. So I'll go ahead and pull up Desmos. I'll turn off the last one, turn on this one, and that's supposed to be a negative 9. Sorry again about that. So once again, this is a crazy looking graph. If I zoom out, we're just going to focus on where it's crossing the x-axis, and that's happening here at negative 2.708, which is exactly what we saw, and negative 13.292, which is exactly what we got. So I wanted to show you this just for the visual of checking your solutions, but once again, for a test without a calculator, this is as far as you could go, or you could show both of those together like this with the plus and the minus instead of separating it out into plus and minus. All right, we're going to look at 2 last examples for solving using square roots. So one of them is going to be 3 times x minus 2 squared equals negative 72. So I'm noticing this is an example of an equation in vertex form or transformation form. So I'm just going to think about order of operations, SAD/MEG. So the S and the A stand for subtraction and addition, which I have, but they're trapped inside of those grouping symbols. So I'm not going to be able to undo that just yet. So then I'm going to move on to D and M, so division and multiplication. I'm noticing this means 3 times all of this. So I'm going to do the opposite, and I'm going to divide by 3. All right, if I think about SAD/MEG, now we're at E, which is exponents, and the opposite of squaring something is taking the square root. And this is where I just have to remind myself that there are 2 solutions that come from that, a positive and a negative. So when you get to the point where you're taking the square root of both sides, just add that in to remind yourself. So squares and square roots will cancel out. I'll have x minus 2. And I'll have positive and negative. And I want to think about how to simplify this radical. So I'm just going to do that off to the side. The first thing that I'd want to think about is the square root of a negative. I can change that to the square root of negative 1 times the square root of 24. That way I can go ahead and just replace the square root of negative 1 with an I. So this is going to be an example of imaginary or lateral solutions. They'll exist in 3-dimensional space. Next, I want to find the biggest perfect square that divides into 24. And if I rewrite that, it happens to be 4. And so now if I take the square root of 4, that's going to give me 2. So I have 2 and I outside the square root sign. That 6 would still be on the inside. So I'm going to go ahead and replace 2i root 6 with that square root of negative 24. So we simplified it off to the side. We figured out what it simplifies down to be. So I'm just replacing that now. Finally, to get x completely by itself, I would want to add 2 to both sides. And I'm noticing this is not a like term with this. It doesn't have the same variable, so it doesn't have an I. It also doesn't have the same radical. So in this case, I would need to just say that that positive 2 is being added and subtracted from 2i root 6. I can't actually combine them together, so I have to leave them separate. And for a test, this would be as far as you can get. If it helps, you can write it as 2 separate ones. You could say 2 plus 2i root 6, and you could say 2 minus 2i root 6. But that means the same thing as this. It means plus and minus 2i root 6. So if we look at this graph, I'm going to jump over to Desmos. Turn this one off. turn this one on. If I look over at this graph, where is it? Okay, this one is not working. Sorry about that. I don't want to spend too much time on it, so we're just going to go back to our last example and finish up. But this would be a graph that looks like it's not crossing the x-axis because it has imaginary solutions. So that's happening above our paper. That's happening in three-dimensional space. So one last example would be something like this. So I'm noticing this is an example of one where we don't have an x term, we're missing b. So this is where I can solve using square roots. So I just want to keep thinking about inverse operations. So SAD, MEG, S, and A, I'm going to deal with addition and subtraction first. So negative 13 minus 3, that's going to be negative 16. All right, next I'm going to move on to D and M, division and multiplication. This is 2 times x squared, so I'm going to do the opposite. I'm going to divide. And finally, to undo exponents, the opposite of squaring is taking the square root. And I just need to remember that there are 2 possible solutions that come from that, a positive and a negative. So squares and square roots will cancel out. And I want to simplify this radical as much as possible. So if I think about it off to the side, I can do the square root of negative 1 times the square root of 8. And that way I can change that square root of negative 1 to I. And then I want to look for the biggest perfect square that fits into 8, that divides into it. And in this case, it's 4. We just happen to have a lot today that were 4. And so if I simplify this now, the square root of 4 becomes a 2. That I was also on the outside, so those will still be there. And then the square root of 2, 2 is not a perfect square, so I'm just going to put that back in. So I would have positive and negative 2i root 2. And once again, if you don't like leaving it like this, you can write it as your 2 separate solutions. You could say x equals positive 2i root 2 and x equals negative 2i root 2. And on a graph, this would look like it's not crossing the x-axis because imaginaries are a third axis. They exist in 3-dimensional space. All right, so that is it for today. Feel free, I'm going to link this video on Schoology so you can look back at any of these and kind of stop and pause anywhere you need to. And then your homework for tonight is on Desmos.